So we've discussed diffraction at 1 and 2 slits. Now what we're going to look at is a device that was invented in the turn of the early 1800s, and it's called the diffraction grating. Now a diffraction grating is essentially a sheet which has many slits on it, and we rate diffraction gratings as the number of slits per meter. So the higher the number of slits per meter, that means of course the closer these slits are together. So to have a look at the pattern that we're going to expect to get from that, let's go back to Huygens principle. So here's the situation we've got with a diffraction grating. We've got an infinite number of slits. We're stretching off in both directions. So what we've got is each of these slits acts as a point source. So we're assuming here that we have a point source of waves. So we're not integrating over the wave, the length of the slit here. We're assuming it's a narrow slit, just like we did for 2 narrow slits. And we're going to assume that we have a separation between 2 adjacent slits of d. And so when we're looking at the rays that are coming out at a particular angle theta, again, of course, we're doing this far field approximation where the screen is a long way away, so all these rays are parallel, then we're going to end up with a difference in path length of d sine theta between adjacent slits. So this means that we're going to have a wavelength, contribution from the nth slit that will look as, it'll be a e to the I, and then we're going to have our kr minus omega t, and then we're going to have added onto it, because of course each additional slit adds this extra d sine theta, so we're going to add on to that plus kn times d sine theta, where n now is the slit number. So what that means is that we're going to have each additional wave is going to have so the phase difference of the nth from the nth slit is going to be equal to knd sine theta. So we're going to have waves, an infinite number of waves if we're assuming an infinite diffraction grating, and the phase difference of the nth slit compared to the first slit is going to be given by knd sine theta. So let's have a look at this. What we're going to do now is we're going to plot these on a phasor diagram. So if we remember back to when we were doing oscillations and we talked about phasors, then here we have our real axis, here we have our imaginary axis, and we had a phasor was representing a line essentially that point out to a circle. They all have uniform length, and this angle here gave us the phase, and so this angle here will be for the nth slit, the angle that this phasor will make will be knd sine theta. So these phasors for additional slits will all be evenly spaced. So I can imagine if I try to draw these evenly spaced out, these are going to be the phasors that we get from all of these slits, and each of these incremental changes here will actually be just, now I'm removing the n, so it will be just kd sine theta. So this will be kd sine theta, and this will be, so this is the first slit points along here, so this is slit 0, then slit 1, slit 2, slit 3, slit 4, and so on, and of course eventually we'll start to loop back. So rather than try and draw all these arrows, what I'm going to do is I'm just going to draw a circle with a number in it to show you where these phasors point. So here we have our diagram with these dots representing the phases of the different slits. So this is phi 1, this is phi 2, the phase we get from slit 2, and so on and so forth. So what happens as we go around, this is the general case, and so in the general case our phase difference is not a fraction of pi. So this means that we don't ever really add up or line up precisely with any other phase. But because, of course, in this limit that we have an infinite number of slits, we're going to be doing this an infinite number of times, then when it adds together, we're just going to get a ring of phases that are uniformly distributed all the way around this circle, because each time we go round, we end up with some random location on the circle, even though they're evenly spaced. And so we end up with this random ring, a solid ring of phases. And so the sum here, if I add up all the vectors, remember they're all coming from the center and they're pointing out to this edge, if I add up the sum of all these, I get 0, because the ones that are pointing here are precisely cancelled with the ones over here, and the ones over here are cancelled with the ones over here. And if I do this an infinite number of times, these points are randomly distributed on this ring, and so I'm going to be able to get an even, I'm going to always get a perfect cancellation. So that's if we don't have, if this phase difference is not a fraction of pi. Well, supposing the phase difference is a fraction of pi, so here let's say delta phi is equal to, well, in this case, 3 pi over 2. So I start here for my first phase, I go round 3 pi over 2 and I get to here. Then I go round 3 pi over 2 and I get to here. Then I go round 3 pi over 2 and I get to 4, and I go 5 over 2 to 5. And what's going to happen is I'm going to start building up all of these phases here. Since I'm doing pi over 2, they will be always separated by pi over 2. If I just did 1 pi over 2, of course I'd have them all the way round, and then I go round again on the inside. So what will happen here, of course, is that I will get an even, the ones here will cancel with the ones here, and the ones over here will cancel with the ones over here, and so again my sum will add to give 0. So if I have something that's not a fraction of pi, I get 0. If I have something that is a fraction of pi, I also get 0. So do I ever not get 0? Well, yes, if delta phi is an even multiple of pi. And if I do that, this is what I get. So I start with my first phase here, this is phi 1, and then I go round by 2 pi, or 4 pi, or 6 pi, or any even multiple of pi, and I get back to here. And then I go round another 2 pi, or 4 pi, or 6 pi, whatever the value of n is, and I get back to here, and so on. And here what happens is that my sum, if I add up all of these phases, will give me one very large phase pointing in this direction. In other words, the waves from each slit in the diffraction grating will arrive at the screen with exactly the same phase, and so since they will arrive with exactly the same phase, they will add together constructively, and I will have a very bright line at that point. And at any other point where this is not true, then I will end up with perfect cancellation, and I will end up with a dark spot there. So my condition for constructive interference from a diffraction grating to get a bright line is 2n, is this phase difference between each adjacent slit has to be some integer multiple of pi, and the phase difference between slits, if you remember we said, was kd times sine theta. So what I want to do now is expand this out. So I have 2 times n times pi, and k I can write out as 2 pi over lambda times d sine theta, and so I can just cancel the 2 pi on both sides, and so I am going to get constructive interference when sine theta is equal to n lambda over d. Now d here is the slit separation, but since we're dealing with thin slits, the number of slits per unit length, so n is equal to the slits per meter in this case, if I'm using SI units, then n here is just 1 over d. And this is actually what we rate diffraction gratings as the slits per meter. if we're using SI units. So if I write it that way, then my condition for constructive interference is that sine theta is equal to n times lambda times big N, right? And so this is when we get a bright fringe, a bright line. Now the thing to note here is that this very much depends on the wavelength of the light, and of course since n here can be different values, so n here can be 0, 1, 2, 3 and so on, we will end up with various maxima depending on the value of n. So let's see what that looks like if we plot the intensity function. So here we have the intensity function from a diffraction grating, and this has got 800 lines per millimeter, the units we've used here, and we're shining on it light with a wavelength of 500 nanometers, and if you do the calculation, this means that you should get a spacing of 0.4. So this distance here in sine theta is 0.4, and so this is where we have our little n is equal to 0, this is little n equal to 1, little n equal to 2, and so on. So we end up with just a line here at this point, and nothing anywhere else, because in these places the phasors cancel. Now this is the case for a diffraction grating with an infinite size, but obviously we can't build infinitely sized for diffraction gratings. So what happens if we have a diffraction grating with a finite width? So here is the pattern we get for a finite width diffraction grating. And so what we're seeing here is that instead of these narrow lines, we end up with this is in fact the single slit diffraction pattern. And this single slit diffraction pattern is based on the width of the grating. So if we have a grating width, so if we imagine that we've got, say for example here, this is our diffraction grating, and we've got all the slits in the diffraction grating here, then this separation here is based on the number of slits per unit length, and if this is the width of the grating here, W, then this, the width of this slit here depends on W, and in fact in this case it would be 2 lambda over W, just like we had for the single slit width. The width of the central maximum was 2 lambda over A. And so the fact that we build finite diffraction gratings limits how accurately we can actually measure a spectrum of light, because each wavelength will have one of these peaks, and obviously if we have two wavelengths that are closer spaced than 2 lambda over W, we won't be able to resolve them as two separate wavelengths, because the width of these peaks will cause them to merge. However, we can make the width of a diffraction grating can in fact be several centimeters, and remember that the wavelength of light is measured in hundreds of nanometers. So in practice, diffraction gratings are a fantastically good way to resolve the spectrum of light. So just as we did for the slits, here we have our coherent source of light, our laser, and it's firing at a diffraction grating. And what you can see on the screen, there's no need to even zoom in at this point, is you can see a whole series of dots. And these are the angles at which we get that coherent interference that adds together to give us a single bright spot of light. And since the laser is a monochromatic source of light, we get a single point corresponding to the wavelength of the green light that the laser produces, which is 543 nanometers. So this is a diffraction grating with 2,500 lines. It's an American one because it's lines per inch. But what we're going to do is we're going to increase that now, and I'm going to put in front of it a diffraction grating with a far larger number of lines per inch, by about a factor of 3. So you've seen the diffraction pattern we get from that. Now if I slide this one in, you can see that with this narrower spacing of the lines, so more lines per unit length, we end up with the dots being further spaced apart. And in fact, if I put in the one at the top here, which is 15,000 lines per inch, you won't even see any of the dots in the screen. They'll be so far apart. Well, maybe just one dot on the screen, and if you look carefully in the background behind, you can see where the other dots have gone. So as we increase the number of lines per inch, or the number of lines per meter rather, we increase the separation of these dots. So we've seen how a diffraction grating can separate out a wavelength of light into various maxima at various angles. But what we showed before was a monochromatic source of light, a laser, and of course that only has a single wavelength, and so we only get single points of light. But what we've got here is a projector that is generating white light, and in front of it we have a diffraction grating. And if you look at the screen, what you can see is a whole series of spectra being produced with a white line right in the center. Now, what's going on here is at the center we have a central maximum, and it doesn't matter what the wavelength of light is, we will always get a maximum right in the center at 0 degree reflection, independent of the wavelength. And so since we're shining white light here, we end up with the white light, all the different wavelengths going through and producing the maximum in the center. But as we move away from the center, the next maximum occurs at an angle that depends on the wavelength of the light. And since we have a whole series of different wavelengths being produced in this projector, which is what constitutes white light, you can see that we end up with a whole spectrum of colors. And what you can see is that the blue light is closest to the white light in the center. That's because blue light has the shortest wavelength, and the shorter the wavelength, the less the diffraction angle that will be produced. So if you look on both sides, you will see that blue is closest to the white line in the center. Whether you go off to the left or off to the right, it's always blue that's closest, and red, having the longer wavelength, is diffracted through the larger angle and occurs on the outside of the spectrum. Now, that's great for white light, but this was a fantastic tool that was put to great use in the early 1800s for studying the spectra of different objects. And in fact, it was Fraunhofer who turned the diffraction grating to the skies and started to look at spectra from distant suns so that they could study the physics of the light that was coming from these remote objects. And they found, in fact, that the spectra was not the same as the spectrum produced by the sun. When they turned these diffraction gratings on the sun, they saw that there were certain absorption lines, and these lines were in fact called Fraunhofer lines. And this led to the discovery of a new element, the element of helium, which is named from the Greek god for the sun, Helios. The other thing, and this is what led to a revolution in physics, is what happened when they turned this diffraction grating and analyzed the spectrum produced by different elements. And this produced an enormous surprise from what the expectation was. So to show the impact that the diffraction grating had, what we've got here is a series of different elements. So we've got argon, neon, mercury, hydrogen, and helium. And what we can do is we can pass an electric current through these elements, and when we do that, they start to glow with a characteristic light that is particular to that element. Now, what we can do with a diffraction grating is we can take that spectrum of light that's been emitted and we can break it down and observe the individual wavelengths of light. So to show you what I mean with this video, what we're going to do is I'm going to turn this on, and you can see that helium glows with a yellow light. And then if we put a diffraction grating in front of the lens, what you can see now is you should be able to make out that there's some lines being produced from the spectrum of helium. Now, this isn't ideal because, of course, there's also light coming from the background that's passing through the diffraction grating and also being diffracted, and so you get a bit of a noisy image that isn't particularly clear. However, if we turn the lights out and take some photographs with the diffraction grating in front of the camera, you can really see the individual lines that make up the spectrum of all these different elements. So here you can see the helium spectrum. On the top there is just a standard photograph of our helium tube emitting the yellow light. On the bottom, what we've done is we've taken a photograph with a diffraction grating in front of the lens, and you can see that this separates out the spectrum of light. In the center, we can see that we're going to have a maximum from every line in the helium spectrum, and so we get the yellow helium light, just as we had in the ordinary photograph. But now off to both sides, you can see that the spectrum of helium consists of certain particular wavelengths. So starting closest to the center, we can see that we get a violet line, and then a blue, and then a green, and then there's a broad yellow line, and then some red further out. And on the other side, you can see again the same spectrum and the same lines, but now inverted, so that the violet line is always closest to the center. And so the surprising thing when we look at these lines is that we get lines. It's not a continuous spectrum, it's particular wavelengths. So this is helium. Let's have a look now at hydrogen. So here we can see the red glow that we get from hydrogen, again at the top with a standard photograph, and then underneath when we look through a diffraction grating. And here we can see a spectrum with far fewer lines. Close in there's the blue, and then there's a sort of a light blue, and then finally a red line. And in fact, hydrogen has a predictable series of lines, and hydrogen was in fact the first spectrum with lines in it where people noted a pattern. But again, the surprising result is that although we have fewer lines than we did for helium, we still have certain fixed wavelengths of light being generated, and we can see that very clearly when we look through the diffraction grating. And this was really the first time that people have had the opportunity to look at a spectrum. The diffraction grating was the first way that they had to separate out a spectrum into very particular wavelengths. And so here's the last spectrum that we'll look at. This is the spectrum for mercury, and as you can see in the standard photograph, it's a white light. And in fact, mercury used to be used in street lighting before the recent switch to sodium. Now, if we look at it through the diffraction grating, what we can see is that this bright white light is actually formed from three different wavelengths, one blue, one green, and one red. And again, we can see these three particular wavelengths of light when we look through the diffraction grating. So it's clear by now that it's not just one element that produces these particular lines, but every element out there produces a spectrum that has only certain fixed wavelengths. Now, this discovery of lines in every atomic spectrum was an astounding breakthrough. What it showed was that only certain wavelengths of light were emitted. And yet, when we look at something like the sun or an incandescent light bulb, we see a continuous spectrum. So there was a big mystery in physics as to what was going on that caused all these different elements to emit at only certain wavelengths. And solving that mystery led to a fundamental paradigm shift in our understanding of physics. It led to quantum mechanics.